All right, let's see. Let me see if I can disable the Zoom notification. Can you all hear me? See, I think there's a bit of stream delay. Okay, I'm getting a yes in the chat. Yeah, I guess just put a message in there if you can hear all right. Just want to make sure that everything is working before I start the stream. Okay, perfect. Let me check the, what does it say finished? Oh shoot, it's not on the sidebar anymore. Okay, yeah, I'm gonna fix that then. Kostav asks, will you be telling solutions too? Yes, I'll go over solutions after the contest is done. And I'm gonna go, give me one moment, I'm going to make sure that I'm gonna try and put this back in the sidebar. Let's uncheck finished, see if that works. Okay, looks like it is back on this sidebar on CF. Alrighty, perfect. So I think we're ready to get going. Something new that I'll be doing today that I haven't done in any of my videos yet is I'm going to be doing my scratch work on this iPad, and I'll have it pulled up here so that you'll be able to see what I'm doing. I'll try and have it up whenever I'm making notes about the problems, and so as I write, you will be able to see it right here. So that should hopefully be interesting. Obviously, most of it during the contest is going to be random scribbles. Normally, my notes are not particularly well organized, but hopefully, oh, let's see, it says the bitrate is low. That's not good. Okay, let me give that a moment. If there are any quality issues, let me know in the chat, and we can get that figured out. I'm going to pull up OBS real quick, just to see if there's anything that I need to do. Let's see. Is there a way to change the bitrate? Yes, okay. All right, we'll see if that changes anything. But yeah, as long as if the quality is all right, then I'm not too worried about it. But if there are any issues, then let me know. But okay, I mean, I think for now we'll just go ahead and get started with the contest. So I'll set up a virtual participation. Let's see, don't want to wait that long. Let's start at 1:06, and here we go. Got a minute 20 to kill, so if people have any questions, in the meantime, let me know. LGM win, hopefully soon. That could be a tough one, but I don't know, hopefully before too much longer. I'm hoping to return to Div 1 competition before too long. Before too much. Oh, oops, okay, yeah, quality looks fine. Is it going to be under 30 minutes? Probably not. I mean, one can dream, but I don't know. Optimistically, I'd say about an hour. Likely, you know, maybe more like 90 minutes. We'll see. I don't know. I'll do my best, but I don't know. I don't really know how long it's going to take. Justin says, why haven't you been taking contests recently? I had a really good performance in March. Solved a 3200. That pushed me up to 2873. And I felt like that was above my true average performance, so I've just kind of been content to stay there for the last couple of months. So I've just been chilling at 2873, but I don't know, I'm feeling like I'm getting to the point where I'm ready to get back in the game. Okay, so contest is starting. Let's give this a go. Okay, so the observation here is that we should pick two adjacent values, I'm pretty sure. Because that's always going to, because that's never going to, yeah, that's definitely right. I will run it on the samples just to make sure. 8, 12, 6. Okay, yeah, this looks good. All right, great start. Okay, find the maximum value of I times j minus k times a sub I, or a sub j, or, Okay, that's interesting. Okay, so the thing on the right is at most, I'll pull my scratch work. It's at most 100n. So we only need to check pairs that are at least n squared minus 100n. And there are at most 10,000 of those, which seems all right. Okay, yeah, let's try that. Okay. Yeah, so this n squared time. I'm just gonna do this just to be safe. Okay, so cur minus k times a of I bar a of j. Oh, actually, it could be negative 1. Let's just set it to negative 1 e12 to start. Oh, and I and j have to be distinct. In fact, I can actually set it up like this. Okay, negative 1, negative 4, 3, 12, perfect. I have relatively limited confidence in my implementation here, but it'd be nice if this was correct because I feel like I came up with that one pretty quickly. Test 10. Okay, I'm gonna assume this is right. All right, find the mechs of the XORs. Okay, mechs of n XOR up to n. Okay, test 45, there's no way that fails. Okay, this is interesting. So if the most significant bit of n is let me pull up. Okay. Okay, accepted on B. Perfect. All right, so okay. Okay, so we can assume m is greater than or equal to n. I'm going to look at D real quick. It's worth about the same number of points. Each non-empty substring occurs an odd number of times. Okay, that's interesting. Yeah, I don't really have any immediate ideas on either of these, so it could take some thought. So I guess for this one, I'm kind of tempted to just do like some sort of DFS sort of thing. Seems like it could be pretty annoying. Okay, so that's pretty interesting. Okay, I think I see how to do this, possibly. for the suggestion. I should indeed use parentheses. That would be highly advisable. I feel like I might have written this wrong. Okay, let me just try this first case. Okay, that should not be happening. Okay, so 4, 6. Oh, I see. Yeah, this is if n equals 0, and then I don't think I need to worry about the rest of this. Okay, perfect. Ah, shoot, okay, it's wrong on this last case. I feel like this kills way too much time, but I'm kind of tempted to write a brute force and find a smaller counter case, which I think is what I'm going to do. Why isn't this? Okay, yeah, that would do it. Okay, there's an error. All right, oh, I think I might see the issue here. I'm handling this case wrong. Okay. Let's try it like this. Okay, so now that's still wrong. Let's see if I can fix this. Let's see, is it just this case that's wrong? Or wait, what was it? Was it 5-7? Yeah, 5-7. I see. Okay, so there's one more little edge case. Oh, stop. I feel like this is taking far longer than it should. Can I stop my screen? Okay, there we go. Alright, so there. Oh wait, I need to actually test on the sample again. Okay. So I'm gonna assume this is right now. Not that I'm not happy at all with how long that took me, but not much to do about that. Just gotta hope I can do D faster. Okay, every substring occurs an odd number of times. So what I'm kind of tempted to do is yeah, I'm gonna try this. Okay, so what I'm doing here is I'm just gonna write a brute force to check every substring. or to check every possible string with n or with length n using the first k characters, and I'm hoping that'll motivate the pattern. What do you mean n wasn't declared in O? Okay, why doesn't this work? Oh, I'm not calling my method. Okay, so for 3 we really do need 3 characters. Do AA, BA. Huh, okay, so we can do 10 with 2. Do all the evens just work with 2? Yeah, I guess I do. So, okay, so alright, so we got the even case down cold. That's easy. Alright, so now I just need a pattern for the odds. So for 5 we need at least 3. Or for 5, yeah, for 5 we need at least 3 A, B, A, C. Oh wow, okay, this is really easy. I'll talk about this more at the end, but this is why for a problem like this, you always, every single time, wait, why am I even reading the string? Every single time you check for a pattern using a brute force rather than trying to come up with it yourself. Well, should have done this before C. That's for sure. Yeah, writing a brute force is one of the most underrated techniques in... Oh, well, it's wrong, but... Let's see, I'm wondering if I handle an edge case incorrectly. Oh yeah, I do. Alright, well, I'm stupid, but that is alright. Yeah, it would have taken me a very long time to come up with that on my own, but took all of 5 minutes. Oh, wait, how is that still wrong? Shoot, okay. Writing a validator here. I guess I can reuse my check method from up here. Oh my goodness, I forgot to... No! Okay, still the n equals 1 case? Wow, I'm so stupid. This is why you always test before you submit. Since I already have this... ready, I'm just gonna validate just to make sure. Okay. Oh, I can't believe that I'm... Yeah, this is not my day. Not at all. Yeah, there we go. Okay. Well, gonna have to make up for it with a really good time on E. I've not been reading chat, by the way, to avoid spoilers, so I will read up, but everything that's in chat I will read later on before I go over solutions at the end. Alright, select an unerased node U. Assign AU to be let AU be the number of unerased nodes adjacent to U. Erase the node U along with all edges that have it as an endpoint. And we need to do this by GCD. Okay, so there's obviously a principle of inclusion-exclusion element to this problem. Okay, so first of all, the order really doesn't matter, so let's just multiply by n factorial at the end. And then the second thing is that we can do a principle of inclusion-exclusion thing using the Mobius function. Actually, wait, hold on. So in the first test case, oh wait, hold on. Wait, I think I'm misunderstanding this. How can we select an unerased node U n times when yeah, how can we select an unerased node n times when there are only n nodes and we erase... Oh, we erase all the edges. Not the nodes connected to it. Okay, no. Scratch all of this. I've misunderstood this whole thing. Alright. Well, I don't know. I still kind of like the Mobius function idea, but... Actually, hold on. Let's see. Is there a way to do this that'll make the counting a little nicer? Let's see, what's the cleanest way to do this? Actually, no, what am I doing? We can just abuse the harmonic series bound. So yeah, this is a fine dp formulation. Actually, does this work okay? Yeah, I think this is going to be all right. Multitest is going to be kind of annoying here, though. I think I'm going to one index these DPs. Let's see, I think there's another detail I have to work out. I'm not going to need to use NTT here, am I? It seems like that'd be way too slow. But that's kind of where I'm headed. And that definitely would explain why they use that particular modulus. Yeah, I think I'd better use... I think we're going to need to use NTT and make sure that I know how this works. Okay, so... And unfortunately, I haven't written my NTT class to be compatible with my MI, so I think I might just need to go without my MI class for now. Okay, I'm gonna try writing this, I guess. Okay, so first part is easy. It's like literally every other DFS ever written. Alright, so now things are going to get a little bit harder. So QV0. Okay, wait, I need to actually do this in an intelligent way. Because otherwise this is going to be... yeah, this could be too slow. Okay. Okay, there we go. I think that should do the trick. I also need to deal with the edge case for one of the, let's see, how do I deal with the zeros? Let's see, so it's weird. It's hard to deal with the leaves in a way that makes sense. I also worry a lot that this is running up against the time limit. Actually, probably not, because it's 5 seconds and it's only up to 1 E5. I guess there can be 3 test cases, though, so really it's about 5/3 seconds, but... Okay, I guess I maybe see a way forward here. Kind of. Wait, no, this is too slow. Oh, I guess actually one idea is I think we can actually condense the search space considerably. Actually, I don't know if this is really much help, but... Oh, wait. No, actually... Okay, now we're getting somewhere. So now I think if we can get the answer for some fixed k in quasi-linear time, then we're okay. The one thing I'm not sure how to deal with is the ordering. Let's see. Yeah, I guess that's the other issue, is it's not the case that every... Well, actually, hold on. Is it the case that every possible set of ordering can... No, yeah, that doesn't make sense. Okay. Oh wait, what am I doing? The answer obviously has to be a factor of n minus 1. Alright, so then now what? Yeah, I'm worried there's this counting aspect to the problem that I don't really have a great idea of how to deal with. Okay, let's see. So for large potential answers, it seems like it's going to be pretty straightforward. Actually, maybe not. Hmm. I feel like I'm making this harder than it has to be. Okay, so actually I think I'm getting somewhere. So given an answer, I actually think that, given an answer greater than 1, I think I can construct, I think given an answer greater than 1, I can construct the implication graph of like what has to come before what. And so then I need to count the topological sorts, but the problem is that I do not know how to do that, and we're going to need to rely on some special property of the graph because counting topological sorts is, I think it's NP hard in general. And I wonder if there's the fact that this is not exactly a tree, but it's kind of a tree. I wonder if that's helpful. Yeah, I mean the unfortunate thing is that this like implication graph doesn't really have the nice properties that a tree usually has because some of the edges could be directed to parents. Oh, actually, I wonder if we can use the fact that there are no undirected cycles. Not just no directed cycles. See, structures like this are still kind of messy to deal with, though. Yeah, I think I'm still an observation away because I don't think just counting these topological sorts is feasible. Hmm. Oh wait, hold on. What am I doing? We only care about the different sequences. We don't care about the order in which the operations are performed. I think that makes this so much easier. What am I doing? Okay, so... Yeah, wait, so actually the number of sequences for... Yeah, the number of sequences is 0 or 1. And then, 1 is just n factorial over 2 to the... Wait, no, hold on. These aren't guaranteed to all be distinct. Okay, so we just need to... So for 1, we just need to count the number of distinct sequences total. And for this, I actually think we can use a similar idea. Yeah, okay. Alright. So I'm just gonna make a new file because I'm going to be deleting a lot of this code. For starters, goodbye NTT. Actually, let me make sure that all the sequences that I'm thinking about are actually achievable. Yeah, I guess they should be. test. Okay, so that's obviously wrong. Oh, I'm realizing I don't really need this other DFS method. I could just count the number of leaves. Why is that chew? Oh wait, no, it should be chew. Yeah, there we go. Okay, I'm pretty certain. Here, actually, let me... Yeah, no, I actually don't feel like testing this. I'm just going to submit. All right, looks like it passes. I guess we'll give it a moment more to see. Why are there so many test cases? I'm actually surprised it took that. I guess all the GCD operations add up, but okay. Cool, so that's a round. Alright, 16th place, I mean, and probably going to be passed by a decent number of people. Not terrible, but I definitely feel like I could have done considerably better. I mean, obviously, I'm actually going to pull up a private window and see where I am on the actual leaderboard. Because I do think I probably didn't get penalized quite as hard for WAs but on there, but I also feel like people could have passed me, so... Okay, 17th. Alright, I mean, that's not bad. I definitely... Well, first of all, I definitely feel like I should not have had those WAs on D were quite dumb. This is why you test edge cases, and that alone would have catapulted me up to 11th. And then from there, yeah, I mean, from there, I just should not have... both C... I don't know, C was a tricky problem, but E, I definitely should not have spent nearly as much time on. Alright, so I'm going to go ahead and update my stream on Codeforces just to indicate that I'm going over solutions now, and then we can talk solutions and do a quick Q&A. Okay, let's see. Okay. Here we go. Alright, I'm going to see if there is any interesting questions in here that I missed because I wasn't reading chat. I am proud of my time on B. That was pretty nice. Purple Cran asks, I wonder if he'll misread E. Yep, I sure did. He asked why I'm using NTT. So this obviously didn't end up being necessary in the end. But initially I had to use NTT because I was trying to count the number, or I was trying to count the number of ways such that, or to deal with the subtrees such that in exactly k of the subtrees I kept the parent edge, and in the rest I deleted it. And that's something that doesn't really work out, and that's something that normally you would do with a DP, but it would take of k squared time. And so yeah, and so for this in order to keep track of what I was trying to do, you would need NTT. But again, I was overcomplicating the problem. I don't feel like I misread the fact that the order of operations doesn't matter, but I also don't think I really internalized it. And so I spent about an hour on this problem, and I would say at least half of that was on a significantly harder problem than the one we were actually asked to solve. because you'll notice, like, obviously I had a ton of pages of scratch work, but yeah, here's the last page, and let's see how far we have to go back to find the first part where I wrote the key observation. Yeah, here we go. This is the important part. So I'll go over this in more detail later. Actually, let me see if there's anything in the chat, and then if not, I'll just go ahead and go through this problems in order. Okay, yeah. Oh, and Gaurav Raj asked if I can share my VimRC. Sure, I'll do that right now. If you're interested, I'll point you to another video on my channel called My Competitive Programming Setup, where I go over this in more detail, and there's a link where you can download it there. But here, I can just show you real quick. Again, I'm not going to go over this in too much detail, but just to highlight a few important things. The first bit is just some standard stuff to make the editor more usable. Things like indentation, line numbering, that sort of thing. This is my color scheme. These are some key bindings. So this is bracket auto-completion. This maps JK to escape. This uses my C++ template. These are to compile and run. This is just stuff for LaTeX, and these packages are also mostly for LaTeX. I've got some stuff to make the Windows subsystem for Linux clipboard work. And then this is how I customize my cursor color. Again, if you're looking for more detail and if you want to download this, my setup video has it. I'll also be uploading a new one to highlight some changes that I've made recently. Shiso asks, where can I see the full standings? I can put a link in the chat. Okay, cool. So let's talk solutions. Problem A. So we're given n integers, and we want to find the maximum value so we want to, considering all of the subarrays, we want to find the maximum value of the maximum in that subarray times the minimum in that subarray over all possible subarrays. Okay, so here's the key idea. Let's say we start by picking the maximum value of the let's say that we're going to start by picking the maximum value in our subarray. So let's say that's a sub x. And our subarray, by the way, has to have length at least 2. So L has to be less than R. And when we extend our subarray, when we add a sub x plus 1 or a sub x minus 1, so if we assume that a sub x is the maximum element in our subarray, then extending it is never going to increase our maximum, but it will decrease our minimum. And what that means is that we're going to increasing the length of our subarray is never going to increase our answer. And so an alternative way to formalize this is to say, okay, let's say that we have the subarray a sub L up to a sub R. And again, we'll say a sub x is the maximum within this interval. And let's say that we instead take the subarray a sub x plus 1, and we'll just say we'll just assume x plus 1 is between L and R. If it isn't, we can take x minus 1. Well, in this case, then this is going to be equal to a sub x times a sub x plus 1, or the value of this this subarray here is, because that's the maximum, because a sub x is the maximum and a sub x plus 1 is the minimum. And in this subarray, let's say a sub m is the minimum. This subarray is going to have value a sub x, because that's the maximum, times a sub m, which is the minimum. And since a sub m is less than or equal to a sub x plus 1, because a sub m is the minimum, we have ax am is less than or equal to ax plus 1. And the point I'm trying to make here is, if we have this is obviously just a lot of math that maybe doesn't really mean much intuitively, but the intuition I'm trying to communicate here is that if we have a big subarray like this, we can always improve our answer by taking just two elements, one of which is the maximum, or two adjacent elements. Like so we can take a sub x plus 1 like I've done here, or we can take a sub x minus 1. And so what that means is that we only need to consider subarrays of length 2. And of course, we can do that pretty easily. In my code here, I just iterate over all I from 0 to n minus 1, and I check a of I times a of I plus 1, and I print the maximum 1 is the answer. All right, cool. Let's look at problem B. So we're given n integers and an integer k. We have to find the maximum value of I times j minus k times a sub I or a sub j over all pairs of integers with I and j between 1 and n. All right. So the key idea here is to bound the answer. And what do I mean by that? So so intuitively we want to maximize I and j. And so we're going to want to keep and so let's say, and so when we maximize I times j, let's say we just take I to be n minus 1 and j to be n. Then I times j is going to be n squared minus n. And then since a sub I and a sub j are, I actually feel like my solution should not pass here now that I'm looking at it. Yeah, I feel like the test cases are actually weak on this because I think, okay, yeah, so I actually think the test cases are weak on this problem. Maybe I should, well, I don't know, actually, maybe, I think the test cases might not be weak, but, yeah, the test cases might not be weak, but, the code I wrote is its correctness is hard to prove, so, anyway, I'll show you a solution that I actually know how to prove. Okay. So I times j is at most n squared minus n. And let's say so what we're going to do is we're going to say, okay, what's the least possible value we could get when we take I to be n minus 1 and j to be n? And that's going to happen when we maximize a sub I or a sub j. And keep in mind here, a sub I and a sub j are less than or equal to n. And so what we can show here is, let's say the bitwise representation of n is, I don't know, 100110. It can be proven that the maximum possible value of a sub I or a sub j is 111111. And the idea is that we can get all of these bits equal to 1, and that's going to maximize the value, but we can never have any bits outside the scope of n set to 1 in a sub I or a sub j. And the reason is because there's no number less than n that's going to have any of these bits out in this direction set. So the OR is never going to end up there. And so this value is going to be, I guess, it's going to be less than 2n, because if we multiply n by 2, that's going to shift everything one bit to the left. So it's going to be 1 0 0 1 1 0 0, and so then this leftmost bit is going to be higher. Okay. So what that tells us is a sub I or a sub j is less than 2n. And so k times this is less than or equal to 2k times n. And so if we subtract this inequality, then we have that the value of when we take this I and j is at least n squared minus n minus 2k times n. And since k is up to 100, this is at least n squared minus 201n. Okay, so in summary, what we've proven is that the answer is at least n squared minus 201n. And another important observation we can make is there are going to be relatively few values of there are going to be relatively few values of I and j where we can possibly get a higher answer, because the idea is that if and what I'm going to claim here is if I times j is at least n squared minus 201n, then we know that I has to be less than j. So what I'm going to say is that I has to be at least n minus 201. Because if I is less than n minus 201, or sorry, if I is less than n minus 201, then since j is at most n, I times j is strictly less than n squared minus 201n. And so that means that the value of this pair is less than n squared minus 201n, and so it can't be our answer. And so what that means is that I is going to be at least n minus 201. So there are only about 200 possible values of I, which leaves about at most 200 possible values for j. And now we're at the point where we have, okay, let's say 200 values for I, and we'll say 200 for j. This is a very significant overestimate, or this is like a very significant overestimate, but it's fine for our purposes. So that means that in total there are only 40,000 pairs that we need to check per test case. And with 10,000 test cases, this might not seem ideal, because 40,000 times 10k is 4 times 10 to the 8th, which would run in about 4 seconds. But keep in mind, we're only going to have 200 values we can choose from for I when n is at least 200. And so if n is great, and so if the sum of n is at most 3 times 10 to the 5th, then there are at most 3 times 10 to the 5th over 200 equals 1,500 test cases where n is at least 200. So it actually is more like 40k times 1.5k, which is about 6 times 10 to the 7th, which we can expect to run within 1 second. So in my code, I got a C using a similar approach, except as you can see here, I only capped it at n squared minus 100n. I'm actually not entirely sure why this works. I guess it would be a little bit I think basically what I'm relying on is the fact that this bound is not particularly tight. I just did this bound incorrectly when I was in contest, but of course it might be possible to hack this. But as long as if you change this to 201, then it should be fine. And so here what I do is I just iterate over values of n and over values of j, and as soon as I times j is less than this cap, then I terminate. And but then I set answer to the maximum of the answer, and I times j minus k times a of I or a of j. Let's see. Let me take a look at let me take a look at the chat. Sorry. Okay. Yeah, I don't see any questions. If anyone does have questions, please feel free to ask them as we go. But yeah, let's move on to C. All right. So we're given two integers n and m, and we want to find the mex of the sequence n XOR 0, n XOR 1, up to n XOR m. And obviously this little doohickey here is the bitwise XOR operator. Okay, so the idea here is to do casework on the, if we write n and m in binary, we want to do casework on the length of n relative to the length of m. So, case 1, let's say that the length of n is greater than the length of m. And so, for example, let's say n is 1, 0, 1, 1, and m is 1, 1, 1. Then what I'm going to claim here is that the answer is going to be 0. And the proof is essentially that no value between 0 and m is going to have this bit set. And so any value that we can get by XORing n with something less than m is going to keep this bit. So it's going to be at least, in this case, 1, 0, 0, 0. So we're never going to be able to get 0. I guess an easier way you can see this is that in order to get n XOR something to be 0, that something has to also be n. And so if m is less than n, then this definitely won't be possible. Okay. So now let's say that n is shorter than m. So now let's maybe do like 1, 1, 1, 1, 0, 1, 0, 1. Okay. Now the idea here is that let's see, I'm trying to think about the easiest way to explain this. So okay, let's explain it like this. So what we can think of is we can think about dividing the numbers up to m into blocks of size, in this case 8, or more generally 2 to the L of n, 2 to the length of n. And so we can think about this as 0, 0, 0 to 1, 1, 1. 1, 0, 0, 0 to 1, 1, 1, 1. And then 1, 0, 0, 0, 0 up to m, which is 1, 0, 1, 0, 1. And what I'm going to claim to you is that the answer is always going to be in this last set. So this last value, so this last sort of interval. And the reason that this is true is that if we XOR, is that in each of these sets we have all possible value, or we have all possible cases for the last L of n digits. And so when we XOR those with n, then we'll still have all possible cases. And so XORing this with n is going to get you so XORing the numbers 0 through 1, 1, 1, 1 with n is going to get you the numbers 0 through 1, 1, 1, 1, just maybe in a different order. And likewise, XORing the numbers 1, 0, 0, 0 to 1, 1, 1, 1 with n is going to get you the same numbers, but maybe in a different order. Okay. And so now we just need to focus on this last interval. So let me just copy that over. So we have this interval, and n was, what did I say it was? N is 1, 1, 1. Okay. Now then, notice that XORing the integer, or these integers with n, is only going to change these last 3 digits. And so what we can say is that this is going, or is that the result here is going to be 1, 0, 0, 0, 0 plus the result when we consider only the last 3 digits. So So here, the result when n is equal to 111 and m is equal to 101. And so we've reduced m to a smaller value here. And so let me show you what happens in my code in this case. Here, x is essentially representing 2 to the 2 to the L of n. V1 is how I represent L of n. And so then I add I add whatever part of m evenly divides x, and that's done just by subtracting out the remainder. And then I run my function recursively with n and then with the remainder. Okay. Now, what about when L of n is equal to L of m? So here, let me show this real quick. So here I guess I can continue the same case. So n is 111, m is 101. Okay. So here, notice that in order to get an integer with 0 in this first position, we're going to need the integer on the right, the one that's at most m, to have a 1 here. And so what that means is that so like if we're trying to get an integer 0, 0 up to 1, 1, then the only values of our second number that we need to consider are 1, 0, 0 and 1, 0, 1, and then we'll XOR those with 1, 1, 1. And considering these values is equivalent to saying, okay, let's chop off the first digit of, it's equivalent to essentially chopping off the first digit of both numbers and then going at it again. So we can take off the first digit of n and the first digit of m, and then we get n to be n equals 1, 1, m equals 0, 1, and then we continue recursively. And so that handles all three cases, and in each of them we're going to chop at least one digit off of n or off of m. The one other case I deal with is if n is 0, then the answer is just m plus 1, which we can verify directly. And so, and then the one edge case, if they have the same number of digits, is when m is equal to, or when m is plus 1 is a power of 2, which is equivalent to saying when m is all ones. Then we can verify using a similar step to what I explained in this case. We can verify that every single number up to m is going to be reachable, and so we return m plus 1, or 2 to the power, or 2 to the L of n. Oh shoot, sorry, you can't see my scratch pad. Sorry, I should have brought that back up. Yeah, let's see, I don't think I've been writing that much down, but here, let me re-explain anything that might need explaining. I feel like this one is a difficult one to explain. I'm kind of curious if the editorial does it better, so I might pull that up real quick. Let's see. Okay, this is kind of an interesting approach. They essentially use this property right here, that n XOR k equals x is equal to n XOR x equals k. And so they find the least k such that n XOR k is at most m, and they build that bit by bit. Okay, that's actually pretty clever and probably easier to think through than my approach. I did not think of that, and that's probably why this took me longer than it should have. And so I ended up doing this casework on the length of n. Okay, so let's look at D and E, which thankfully I think I have a better sense of how best to explain. Okay, problem D. Now for this one, I didn't really have any immediate ideas when to start, And whenever that happens, especially on a constructive problem like this, if there's a way to write a brute force, then you should think pretty seriously about doing so, because a lot of the time it can be really helpful to just write a brute force and then look for a pattern. And what I did here, I'm not going to go through the details of this code, but essentially what I did here is I wrote some code to come up with the alphabetically first string of length n using only the first k characters, that satisfies the given condition. And the reason I restricted it to k characters is if n is 5, I don't want it to just print out A, B, C, D, E, because that's not really going to give me much intuition for what I can do when we have n so large that we don't have enough letters. I guess I should explain the problem real quick. Actually, we need to find a string of a given length n, such that each non-empty substring of s occurs in s an odd number of times. Okay, and so I wrote this brute force program, and I ended up just trying a bunch of numbers, and what I quickly realized is we actually, I think that sort of a light bulb went off in my head when I ran 10-2, and I realized that we can actually make this work for a string of length 10 using only the letters A and B, and with 5 A's and then a B and then 4 A's. And so I tried to see if this was something that would work for every even number, and it was. So in general, if n is even, what you can do is you can just put n over 2 A's, then a B, then n over 2 minus 1 A's, and that is always going to work. The idea here is that they're going to be the same, is that any substring containing a B is only going to appear once, and any substring containing, like, let's say, or containing some number of A's is going to appear one more time in this first string than in the second string. And so there's going to be an odd number of times that it appears in total. Okay, I thought so. That gives me the solution when n is even. What happens when n is odd? And so I tried running 5-2, but there's no solution, so we're going to need to bring in another character. And with 5-3, we can see it's the same thing, except we just pop a C on the end. 7-3, same thing, just pop a C on the end. 23. Oh wait, that's 20's even. What am I doing? 19-3. Again, same thing, put a C on the end. So we can just add a C, and then we are good to go. And so then the implementation is pretty quick, although I had a lot more trouble than I should have with the n equals 1 case. That's why I got a couple of WAs, and that's why you always test edge cases. Here I put a C on the beginning. It doesn't really matter whether the C goes at the beginning or the end, and then I just directly implemented the construction I gave earlier. All right. Cool. So let's look at problem E. So we're given a tree with n nodes, and we can construct a sequence of integers by performing this operation n times. So first we select a node we haven't chosen. We're going to call that u, and we let a sub u be the number of unerased nodes adjacent to u, and then we erase u along with all the edges that come with it. And for each integer k from 1 to n, we want to count the number of sequences that we can obtain using these operations, such that the GCD of the a sub I is k. So, all right. There are two observations here that I think are critically important. Observation 1, if any leaf is chosen before its parent, k equals 1. And this is pretty easy to prove. the idea is that a leaf is only going to have one edge to its parent, and if we choose it before its parent, that edge is going to still exist. So that means a sub u is going to be 1 if u is a leaf chosen before its parent. And so at that point, then we are, at that point we have an a sub u equals 1, and that means that the GCD of a has to be 1 because 1 can't have any other divisors. So what that means is that in any case where k is not equal to 1, so if k is not equal to 1, then no leaf is chosen before its parents. The second observation is for any answer k greater than 1, there is only one there is at most one way to build a sequence with GCD k. Or in other words, all the answers except the first are going to be at most 1. And the proof here is essentially sort of a recursive or inductive proof. So let's say that we're looking at a node and all of its children are leaves. Then let's see, what's the easiest one? Okay, so then we know all of those leaves can't be chosen before, or have to be or can't be chosen before its parent. And so that means that when we erase so let me just show you all right here. Let me do an example. Let's say that we're trying to construct k equals 2. 1, 2, 3, 4, 5, and this is the tree we're working with. Well, we know 2 has to be chosen before any of 3, 4, and 5 by lemma 1. And so that means that 2 has to be, or that all 3 of these edges will still exist when 2 is chosen. And so now the only decision we have left is whether to choose 2 before 1 or not, because this edge basically can either contribute to 2's count or to 1's count. And since 2 already has 3 edges and we need there to be a number that's divisible by 2 so that it's even, this edge needs to be taken, or we needed 2 to take this edge 2. So that means 2 has to be chosen before 1. And so if we repeat that process, and so what that means is that we know whether upon processing each vertex, whether it has to come before or after its parent. And so we can essentially say, all right, we can essentially prove inductively, if for all children we know whether those have to come before or after their parent, then we can determine whether the current vertex comes before or after its parent too. And by doing that, we can uniquely determine whether each vertex comes before or after its parent, which then determines the number of unerased nodes next to each vertex when it's removed, which determines the sequence A. And so for any k greater than 1, there's only one sequence that works. Okay, and the final observation is that k is a factor of n minus 1. And the proof of this is pretty easy. The idea here is if k is that each edge is going to count towards exactly one each edge is going to count towards exactly one element of A, because we're going to erase each edge and add it to a value of A exactly once. And so since there's n minus 1 edges in total, and let's say that a sub I is equal to b sub I times the GCD of A, then we know that the sum of a sub I is equal to n minus 1, which means that the sum of, that's a terrible sigma, the sum of b sub I times the GCD of A is equal to n minus 1. And so the GCD of A times the sum of b sub I is equal to n minus 1. And so the GCD of A equals n minus 1 over the sum of b sub I, which has to, and so in order for this to be an, and so this means that the GCD of the a sub I is a factor of our n minus 1. All right. So what I'm going to do, so my overall approach here is I'm going to count the number of values of k greater than 1 that can occur, and then I'm going to count the number of distinct sequences that can be achieved in general. And then I'm going to subtract out the number of, and then I'm going to subtract out the number of answers for k where k is at least 2 from the amount of total answers to get the number, or from the amount of total sequences to get the number of sequences where k is 1. And let me walk you through how I do that. Okay, so this DFS1 counts the number of total ways. Now the idea is, if we're on, is that for each vertex there are two things we can do with it. We can take it before its parent, or we can take it after its parent. And so we have two choices, or if we're dealing with the root, only one, because it doesn't make sense to talk about taking the root before its parent. And so then we just multiply that by the number of ways to deal with this vertex by the number of ways to handle each of its children's subtrees. Unfortunately, this is actually just equivalent to computing 2 to the n minus 1, but I was too deep in before I realized that, and so I accidentally wrote this giant function. Okay, now let's talk about DFS2, because this is really the key function. Let's say that we have some fixed value v, and we're trying to construct an answer that's a multiple of v. Okay, now the idea here is we're going to DFS through, and we're going to figure out this value rem stores how many edges will be remaining when it's time to choose v. So how many of its children we're going to select after v. And if this is a factor, and if this number is a multiple of big V, then we add it to G, which is sort of our running GCD. It's sort of the answer, it's what's going to eventually be our answer. And then we say return true, meaning, okay, we're going to select V after its parent. So we're going to select V after its parent. We're not going to take the extra edge. We're good. Otherwise, we can't have rem edges. If rem mod V is non-zero, then we can't have rem edges in adjacent to V while keeping our GCD divisible by V. And so what we have to do is we have to remove V before its parent so that we keep one more edge, so that we have one more edge at that point. And that's where, when we update with rem plus 1 and we return false to indicate that we're keeping the edge from V to its parent for V. And then I run this once for each factor of n minus 1, and if our eventual GCD really is divisible by V, I say, okay, we can achieve this G. And so then I subtract out all the possible values from our result, and that gets us the answer for k equals 1, and then I just print out the answer for k from 2 to n. All right, awesome. Yeah, so I think that is about all. Does anyone have any questions about the contest? overall, I thought the problems were pretty fun. I definitely did not have my best day here between taking a little too long on C and eventually coming up with a solution that was too complicated. And then on D, on D, I got those 2 WAs because I forgot to test on n equals 1. In particular, after the first WA, I definitely should have tested again before submitting. And then in E, I misread the problem. I thought that the order of the operations mattered. And so that made my life a lot more difficult because at that point, at that point, the problem becomes, I don't even know if it's still possible, but it definitely becomes a lot harder. And I spent quite a bit of time thinking about that version. And so that was pretty unfortunate. But yeah, I think that is about all. So, Soam asks, weren't B and C a little harder than usual? I don't have a great sense of how B's and C's usually are, but I think it'd be fair to say that C was maybe harder than usual. B, well, I guess actually the best way to think about this would be to look at the solve statistics. So let me check here. Yeah, C looks like it was fine, maybe a little on the hard end. There's definitely a huge gap from D to E. But B, yeah, I guess B definitely on the hard end. Yeah, because if only less than, or barely a fifth of the people who solved A ended up solving B, so evidently that is a lot harder. And yeah, someone says that problem ratings are out already. Yeah, we can take a look. What round number is this? Oh, that's weird. They're not in the problem set. Let's see if I can just look at the tags. Yeah, so A was an 800, B was a 1700, which, I don't know, that seems a little high to me, but maybe I'm wrong. C was an 1800, D was also an 1800, and E was a 2600. Alikhan says, some of the solutions use Mobius convolution in E. Do you know what it was used for, and are there any efficient implementations on the internet? So I don't know the exact details of how it would have been used in this problem, but generally the idea here, or the idea for why we would use the Mobius function in a problem like this is so let's say that computing the answers where the GCD is equal to k is hard, but let's say that suppose we can compute the answer when, or the counts when our GCD is a multiple of k. Using the Mobius function allows us to get the counts when our GCD is exactly k. And so that's the idea. It's a similar idea to the principle of inclusion and exclusion, if you're familiar with that, or even to the idea of, like, we're sort of computing. It's not exactly prefix sums, but it's a similar general idea where we're computing, where we're sort of overcounting and then we're subtracting out the bad cases later on. As far as an implementation, let me see if I think CP Algorithms has an article on this. Let's see, maybe not. Yeah, here's the CF article. Does this have code? Okay, looks like there's some code here. So I'll put a link in for this in the chat. Yeah, Soam says, isn't Mobius inversion used for inclusion, exclusion generally? Yeah, essentially Mobius inversion is the logical extension of the principle of inclusion and exclusion when applied to a context where, like, we're working with numbers, but we might be overcounting their multiples or something along those lines. rather than like working with rather than the principle of inclusion and exclusions, where we're working with numbers that can be an element of like any number of up to n sets. All right, awesome. Yeah, I guess I'll give everyone a couple moments for questions, and then if nobody has anything else, then in a minute or so we can go ahead and end the stream. It says thanks for the stream. Yeah, you're welcome. Thanks to everyone for watching. Hope you all enjoyed. If you have any questions, feel free to, actually I don't know if I'm going to upload this afterwards, but feel free to just leave a comment. If I don't upload this afterwards, then you can just write something on one of my other videos. That's fine. And someone says, any chance you'll do the educational round tomorrow? I don't plan to stream to virtually participate in the round, largely because I'm going to do it live. I'll probably record it and upload it if it goes well. I might do a solutions stream though, if there's interest in that. So if people, or because normally I record my participation and then I go over solutions at the end, but I might just record my participation and then live stream solutions after the round, if that is something that people would find helpful, and if there isn't something like that that's already on the stream schedule. Doesn't look like there are any streams scheduled, so I might throw one on there. We'll see. Yeah, so I think that is about all. So thanks everyone for watching, and I guess I will see you next time.